amount of memory compared to only storing the biggest network. We've also looked at feeding those networks from read-only memory, so from non-volatile storage, which takes more time, but again, you can start this ahead of time. There will always be some constraint in here. So additionally, you would need techniques to compact the networks as much as possible. But basically, this is one approach that one could make. And it mostly targets energy consumption and execution time. For your other question, which was on the changes from frame to frame. So we are observing effectively that the changes are very little. And the algorithm that we use to predict which network to use is very simple and only looks at the median of the bounding boxes. So for the current frame, we use whatever network we are using, we predict the bounding boxes. We look at the medium of that, of those predictions, and then we have trained, well, basically we've looked at a number of input videos and decided thresholds, a very simple numeric threshold. If the bounding box is below a certain value, we use the smallest network. If it's larger, we have a second threshold. If it's in between the first and the two threshold, we use a second network, and so on. So we know 3 values that separate the networks. We are looking at more complicated mechanisms to also take into account the speed by which objects are moving, also be able to adapt to background workloads. So if the device is also performing other computations, so that we can dynamically adapt. That becomes a bit more complicated. But essentially, it's a very simple technique, and well, the evaluation shows that it gets it right most of the time.
And sir, thank you, sir. And I have one more question. So it was mentioned in the slide that choice of network is also dependent upon the size of the object in the image, right? So let's say if we have very large object in the image, then obviously a small network can do very well. But when the object is very small, so what kind of network will work? So the smaller network or the bigger network? Because in that case, when the object is very small, we will need a very high precision. So
yes, precisely. So when the objects are very small, then we observed that only the bigger networks can detect them, and the smaller networks don't even realize that those objects are present. So they are just, well, basically there's downsampling going on, and just there's too little information retained to make a prediction. And so each of these networks actually has a minimal size of objects that it can potentially detect. And so that's basically being taken into account by the algorithm by looking at boundaries for the bounding boxes.
And sir, would you like to give any suggestion for detecting very small objects in general? This is a question in general. For example, I work in this machine deep learning. So we are working basically in surveillance. So in the video, we have to detect very small object, like some kind of luggage in the video. And the camera is having a very big field of view. So in that case, the object might be very small. So how do we detect that? Is there any suggestion?
I'm afraid I can't make any meaningful suggestions there. So we've been looking at these algorithms as these neural networks as black boxes. Well, not fully black boxes, but we've not really looked into how to design these networks specifically. So I'm afraid I can't make any meaningful suggestion there.
Thank you, sir. Thank you so much.
So Hans, I have a question.
Sure, Jimson, go ahead. Yeah.
Yeah. So you talked about this time series example where you have 32-bit and 64-bit precision. So we don't have much flexibility in the machines where either we have 16, 32 or 64. So do we have other solutions which is optimum in terms of precision?
Yes, well, so as I said, we're bound by the hardware, and so that restricts the choices we can make. And so the arguments I'm making is that we should we should ideally have hardware that allows us to efficiently perform arithmetic on a variety of number formats. And we know that for different applications, basically any combination of how wide exponents and how wide mantissa should be could potentially occur. And we can find applications for that. And so this is also the case for the time series algorithm. And particularly there, it might be interesting to have number formats that sit in between the single precision and double precision IEEE floating point formats. We can design for that. We can write code that uses that. But yes, the hardware support doesn't exist today.
Thank you.
Thanks for those questions. And many thanks, Hans, for a very enlightening talk, especially for me, who is kind of slightly outside this area. It was very interesting to know about the trade-offs between frontiers and the trade-offs between accuracy and efficiency. So thanks again for that wonderful talk, and a round of applause.
Deepak, can you enable? I am not able to share. I need to.
Okay.
Step to be completed. So make me first.
So how do I, let me just get Santosh to do that.
Make me co-host or host.
Yeah, sure. Okay, yeah, so we'll do the virtual memento thing. So over to you, Jimson. Yeah.
Yes, so thank you very much, Hans, for the wonderful talk. I think you have enlightened about the various precision accuracy of various this thing. So we also a small memento, we will try to ship it either through Deepak or through other means. Thank you very much for your talk.
Thank you for inviting me.
Yeah, so thanks very much, and I think we take a short break before the next session.
Yes,
Jimson, when do we? I think we're slightly run over time, so
yeah, that's fine. We will continue with the session, and
okay,
I will take over. No worries.
Sure.
Seema, are you there?
Yes, sir.
Okay, we will take a 2 minutes break and then we'll continue.
Okay, sir.
Rajan Singh, are you there?
Yes, Sir President.
Okay. Akansha Gupta?
Yes, sir.
Okay, thank you. And Satya Rajendra?
Yes, sir.
Okay. So all four others are here. So Seema will be talking. We'll start with the first paper. In the interest of time, we can start with the first paper. There's an improved recommendation system with aspect-based sentiment analysis. So Seema, you can introduce yourself and start with your presentation. Are you able to share the screen?
Yes, sir. Yes, sir. Now the host has disabled screen sharing. That is the message which I'm getting.
Santosh, we have to enable. Just a second.
Yeah, can you try now? Seema, can you try now?
Yes, sir. Yes, sir.
Yeah.
Sandor, Rajan Singh, Seema Safar, Akansha Gupta, and Satya.
So I'll do that, sir.
Yeah. Yeah.
Sir, are you able to see my screen?
Yes. Please go ahead. You have 15 minutes.
Okay, sir. Okay. Just a second, sir. Good afternoon, one and all present over there. I'm Seema Safar, research scholar from Cochin University of Science and Technology, Kerala, India. And my co-authors are Dr. Babita Roslyn Jose, Professor, Cochin University of Science and Technology, and Dr. Santana Krishnan, Scientist, NPOIL, DRDO. And our paper is entitled as an improved recommendation system with aspect-based sentiment analysis. Moving on to the introduction on what is a recommendation system. So basically, recommendation systems are information filtering systems which seeks to predict the rating or preference a user would give to an item. So in simple words, recommendation systems are systems which is designed to recommend things to the user. So as we all know, nowadays, Amazon's, Netflix, etc., make use of recommendation systems to help the users to identify the correct products or movies for them. Moving on to the problem statement and objectives, starting with the intuition formulation. If you're given a set of users, items, and some observed user item interactions, recommendation systems, basically they predict user ratings based on aspect-based sentiment analysis. So on analyzing, what we understood is that the focus should be given on improving the capability of recommending and predicting items. So in short, the objective is to develop an efficient recommendation system that predicts recommendations considering the aspect-based sentiment analysis. Now, just a glance through the literature survey. As our key areas mainly focused on the recommendation systems and the aspect-based sentiment analysis, we focused on two main categories. One is the review-aware recommendation system and the aspect-based sentiment analysis, where all these three papers mainly focused on attention-based models, and the papers on aspect-based sentiment analysis, they were all based on attention-based LSTMs for aspect-based sentiment analysis task. Moving on to the proposed model overview. From the previous existing system, what we understood is that most of the system relied on attention-based system. Now, as we all know, the main disadvantage of an attention mechanism is that as it is adding more and more weight parameters to the model, this can result in increasing the training time when the sequences are going to get longer. So what if we can build a system that can improve the training time, but without compromising the results of the attention-based baseline models? So the aim of the proposed model is to build an efficient recommendation system without compromising the results of the attention-based baseline models, but by replacing the attention sublayers with a different mixing of tokens, which is called as, and the method that we have followed is we are using a Fourier transform for that. The highlights of the work. Now the model, the main highlight is that since we are replacing the attention-based sublayer, we know that attention is basically a training of a huge number of parameters. So here it is very evident that we are using less number of parameters and we are using a simple architecture for the same. Now, the two core modules of this paper include the aspect-based sentiment analysis part and the recommendation module part. Now, the aspect-based sentiment analysis part mainly focuses on predicting the polarity of the aspect-based sentiment. So basically the input will be a review, and the recommendation module, what it does is it will be predicting the rate of the item, rating of the item from the sentiment polarity that is being calculated from the aspect-based sentiment analysis part. Moving on to the proposed model architecture. This is how the simple architecture looks like. As you can see in the figure, you can see a user review, which is being fed onto two different modules. And this three block forms the aspect-based sentiment analysis part. And this is the recommendation module. And the user review is fed onto an FFT layer, followed by an aspect-based sentiment analysis part and a recommendation layer. User reviews also fed onto a recommendation module layer. And this makes use of the input output from the aspect sentiment prediction part and gives us a prediction of the rating on user preferences. Moving on to the details of each of the modules. The aspect-based sentiment analysis part. Now, this is the architecture or the block diagram of what happens inside an aspect-based sentiment analysis part. Now, the raw input, which is an input review, is fed. Basically, what we're doing is we are classifying our input consists of the input embedding or the word embedding. And the word embedding that we're using is GLOVE, which is an unsupervised learning model. And then we have the aspect embedding and the position encoding so that when we are trying to mix the tokens, it does not affect the working of the system. Now, this is inputted onto a fast Fourier transform layer. Normally in baseline models, what we see is that here we have an attention layer and the training happens inside this layer. What we have done in our work is that we have replaced that attention layer with a fast Fourier transform layer. Now this takes as input the input embedding, which consists of the sequence length and the hidden dimension. Now FFT is basically two-dimensional FFT is what we are focusing on. And we'll be applying a two-dimensional FFT onto the input embedding, where the one-dimensional embedding is fed onto the sequence length, and one-dimensional embedding is fed onto the hidden dimension. This can be depicted by a formula, as you can see here. Now, this refers to the sequence. FFTS refers to denotes the sequence length FFT, one-dimensional FFT, which is applied along the sequence dimension. And this shows the FFTH shows the FFT, one-dimensional FFT, which is applied among the hidden dimension. Now, the real part is extracted and we are neglecting the complex part. Now, this is mainly because we don't want the output layers to get modified. So we are just considering only the real part. And this is appended with the aspect embedding and the positional encoding and fed onto a multi-layer perceptron. Now, the baseline multi-layer perceptron is what we are focusing on to train our learning parameters. So we are inputting a multi-dimensional vector onto this multi-layer perceptron, and this follows a gradient descent algorithm. And this is fed onto a softmax function, which will be taking the key features from the vector that is fed. And this is fed onto an aspect-based sentiment prediction part, which will be predicting the polarity of the sentiment that is being fed onto the block. Now, moving to the second core module, which is a recommendation module. And this is work which I followed from Liu et al. Of 2021. It is an ACM paper. And I've cited the paper in my reference section. And this is the recommendation module. And the recommendation module is a simple module which basically contains a convolution neural network. And now CNN is basically used to capture the semantic information. And apart from that, we are also using a max pooling function there so that we get the key features from the reviews that we get from this part. Okay, and that is connected with the, we are connecting that with the aspect sentiment prediction polarity so that we get the prediction of the rating based on the user preferences. Now, moving on to the experiment evaluation. And our evaluation were based on 3 research questions, out of which the first 2 include how does the proposed module, that is the aspect-based sentiment module, as well as the recommendation module is going, how is it going to help in terms of performance, the current state of the art model. And the last question that we are trying to answer is, how does the improved approach contribute to the overall performance of the model? Moving on to the details. The experimental data sets that we are considering here is standard SEM Eval 2014 laptop and restaurant review data set, and the Twitter data set, which was manually annotated. Moving on to the statistics of the data set, as you can see here, This shows the restaurant reviews and the laptop reviews and the Twitter data reviews, and these are the sentiments. Now we have divided our training and our data into training and test data on a ratio 80:20, and these are the ratio in which we have divided our reviews based on the sentiments. Moving on to the evaluation metric, we evaluated our proposed model on 5 main evaluation metric. One is the precision, recall, F1 score, root mean square error. Now, precision and recall, basically precision, what it does is, out of all the retrieved data, it will be identifying the relevant ones. And that will be giving a ratio of that. And talking about a recall, of all the relevant ones, which is the most relevant, we'll get in recall. And F1 score is calculated based on this formula. And after that, we have done a root mean square error to understand the difference. And this is basically a difference between the square root of the difference between the predicted value and the actual value. And accuracy was calculated based on this formula. Moving on to the exploratory analysis of the proposed work. Focusing on the aspect-based sentiment analysis module, as you can see here, this is my proposed model, and I've done a performance analysis by comparing it with an attention-based, aspect-based sentiment analysis model. Now, this is the aspect-based sentiment analysis part of my module. And as you can see here, this was tested on laptop as well as restaurant reviews, and it shows pretty good results in terms of F1 score, though we are replacing the attention layers. And all these models make use of attention layers. And talking about the accuracy, in terms of accuracy also, you can see that here the proposed model shows equal results because it is not trying to compromise the accuracy results, even when we are trying to replace the attention layer. Moving on to the tuning of the parameters of the proposed model. We have actually tuned in 3 different environments. We were trying to improve the performance by tuning the word embedding as well as the aspect embedding. So actually we performed in 3 different categories. The first category was that we tried fine tuning both the word embedding as well as the aspect embedding. And the second environment is we just kept the word embedding as is, the word embedding that we are using low vector. And the aspect embedding was fine-tuned. And the third environment was we fine-tuned the word embedding and we investigated the results. And on investigation, what we understood is that now the proposed model or the recommendation model was compared with an aspect embedding attention-based LSTM model. And as you can see here, this is showing pretty good results, improved results when we are comparing it with the attention model, which is making use of attention-based recommendation. Now, on fine-tuning both word embedding and aspect embedding, we can see much more better results when we are comparing with the second table. As you can see here, this is also showing good results, but in terms of root mean square error, this is showing a bit increase in the root mean square error in laptop reviews. Now, that is the case with the restaurant as well as Twitter reviews also. So we tried with the third environment, which means we fine-tuned word embedding and we just kept the aspect embedding as it is. Now, on doing that, even this worked perfectly fine with a rating of 0.72 and 0.71 for aspect embedding attention-based LSTMs. So as you can see the result, now the root mean square error is decreasing, whereas here it is 0.75. Now this is there is a slight drop in the root mean square error. Now moving on to the quantitative analysis, which is the final research question of our model. Now, how is the model performing in terms when we are removing the attention-based layer? Now, as you can, for that purpose, what we did is our focus was mainly on improving the training time, not on the results, not any promising results we are getting from when we are comparing it with attention-based models, but on checking the training time. The most interesting part here is that there are not many oscillations, as you can see here. But here we have compared the results with, just a second. Here I've compared the results with 3 models, which were making use of attention-based baseline models. And this is my proposed work. And on seeing the blue line, this is almost similar to that of a logarithmic curve. And there are not many glitches, or there are not many oscillations happening. And from the figure itself, it is clear that the training time and the accuracy is improving on training time, and it has converged very quickly. Whereas when we are looking at the other models, we can see that there are oscillations and it is taking much more time. Here you can see a drop in the accuracy level, and there is much more time to settle down the accuracy. Now to conclude, the proposed model is basically an improved recommendation based on aspect-based sentiment analysis, and we are using fast Fourier transform here. And this shows better results even on replacing attention layer, which is quite interesting. And since attention layer is replaced with a two-dimensional FFT, the parameters which is required in the traditional attention-based layer is not required here. So the highlights of the model include, this is very, it is simple model as the attention layer itself is removed. And it is very clear that since the memory resources are highly, there is a drastic reduction in the memory resources that is being used here, and which shows a logarithmic curve in terms of training time when we are comparing it with other baseline attention models. And as we all know that training time is directly proportional to the number of parameters in the model, thus we can see an improvement in curve. It means that there are less number of parameters that is being used in the model. And last but not the least, we have fine-tuned word embeddings and aspect embedding, and that is showing outperforming values, and that is outperforming the values of unsupervisedly learned word embedding, that is the GLOVE embedding that we are using here. These are my references. Thank you.
So any questions to Seema? Thank you very much for the presentation. So while others are thinking about the questions, I will ask one question. So you said attention-based model are quite complex, and you're replacing with FFT as one means of extracting some information. So did you really check the how much is the complexity is you are improving in terms of parameters?
In terms of parameters, we can conclude that since it is a logarithmic curve, it is of the order log n. Whereas when we are considering attention layers, normally what we see is it is of the order exponential terms, raised to the power n, if n is the size of the input.
You should, this is very high level answer, that is fine, but you should actually look at the actual number of parameters, okay, and see that then only you can justify. And also the other metrics also you may have to consider. And still there is a long way to improve your model, right? We have only 72 or 0.72.
Yes, sir, definitely.
Like the previous keynote has mentioned, you can also try various precision right from 16, because most of the time you may be using 64 point floating point operations in your model, which may not be necessary. So that is maybe one thing you should look at, how FFT is sensitive to floating point 16, 32 or 64. How does the performance changes? That itself may be a good analysis. You can do it. Okay. How precision.
Okay, sir. Okay, sir.
Okay. Any other questions to Seema? Yeah, looks like there is no questions. You can sign out. I mean, you can unshare.
Thank you, sir. Thank you so much.
Rajan Singh.
Yes, sir.
Yeah. So now share your screen and briefly introduce yourself and start.
Sir, I too just got the same mistake, disabled participant screen.
Now it's fine, right? Okay, Santosh, are you there?
Yes, I'm here.
Yeah. So he's not able to share. Rajan Singh.
Rajan Singh. Satya Rajendra Singh, right?
Yes.
Yeah, exactly.
Yeah, but you are co-host now. What's the problem?
No, sir.
You can share your screen. No issues. You have the co-host rights.
I am asking Rajan Singh. Will let us go in the order. Rajan Singh and Prashant K. Srivastava, are you there?
Oh, sorry. Hello.
Rajan Singh, you can present.
Yeah.
Second
So,
paper.
yes, sir. Actually, I'm sharing my screen. Is it visible now?
Not yet.
So, is it visible now, sir?
Not yet. You have to select the right screen. Yeah, now it's fine. You are selecting the wrong screen. That's why.
Okay. Documents. Yeah. So now is it visible?
You share the entire screen, then you select the right tab. Okay.
Actually, I have shared. It is showing over here, like stop sharing and hide in my.
Not visible. Okay, you are selecting the wrong screen.
It is not shared.
You sign out and signing again. Akansha Gupta, can we go next?
Sure, sir.
Yeah, perfect. So you can briefly introduce yourself and start your presentation.
Yes, good evening, everyone. I am Akansha Gupta. I am currently pursuing PhD as a senior research fellow in Delhi Technological University. So, the title of my paper is COVID-19 cases prediction based on the LSTM and SIR model using social media. My paper ID is 24. This is the outline of the presentation. Okay, so let's start with the abstract. So the coronavirus epidemic, which was spread worldwide, has also hit the India and has severely impacted the India as well. So nowadays, the social media platforms are one of the primary sources of conveying the information. When with the coming of the COVID-19 epidemic, there was an increase in the information sharing on the social media platforms. So we have considered various social media platforms for predicting the 19 cases. In our work, we have considered a SIR model, SIR-based model to simulate the COVID-19 cases. In this work, we have considered the impact of the prevention and the control measures and the preventive awareness using the COVID-19 data from various social media platforms such as the Twitter, Reddit, and Google News. The infection rates the deviations in the infection rates are updated using the LSTM model, and using the LSTM model and the PEN LDA model, we have proposed the SIR model in our paper. So the results of our paper have shown that the proposed model is performing well or better than the other traditional models. Okay, so what the background says is that the COVID-19 as the COVID-19 outbreak spread, there was a great public awareness about the COVID-19 on the various internet platforms, and the transmission of the information can significantly impact the people behavior and the efficacy of the government countermeasures. So online news was a popular medium for disseminating the information regarding the COVID-19 updates and also the prevention and the control information. So therefore, there was a need of a study on the emergence and the spread of the epidemics. There were various epidemic models were used to estimate and anticipate the growth rate of the disease, and the results were used to derive the information of the preventive and control measures. The few common models that were used were the SI models, SIR or the SEIR models that were commonly used models, but these models do not contains the government prevention and the control information and the public knowledge in them. So we have considered the availability of the transparent pandemic reporting and the prevention and the control measures that may have an impact on the virus spread. Therefore, we have developed a data-driven epidemic model for the public health crisis. In this way, we have overcome the limitation of the traditional epidemic models that only employ the single component of considering the historical cases. In our model, we have integrated the feature from the COVID-19 related online information along with the historical cases. So this was the model that we have used. This is the SIR model. In this, we have embedded the LSTM network. The differential equations of the SIR models were established as shown on the screens. These were the equations. What we have done, this is the methodology. First, we have collected the data. We have collected the tweets, Reddit post, and the Google News related to the COVID-19 from March 1 to May 16. For the tweets, we have used a Twitter API from the Twippy API, and we have collected the tweets from the account of the Ministry of Health and Family Welfare, Government of India. Next, we have collected the Reddits with the subreddits from the eight various subreddits that are shown on the screen. And later, we have collected the news from the Google search engine using the search term as COVID, coronavirus, Corona, India, and the news. Okay, these were the three sources that we have used to collect the textual data. Later, we have pre-processed the data and removed the duplicates and the irrelevant data that do not contain the COVID-19 related information from all the three data sets. And we have classified all the textual data by date and then average all the features from the textual data according to the date. That is presented as a single textual feature vector for a particular day. These tweets were then converted into the bag of words representation for every particular day, and then they were input into a PEN LDA model, which was a feature extraction model. And from the PEN LDA model, we get the features which for every day we get the feature vectors. So later what we have done, this was the model that is representing how we have merged the two infection data and the textual data. In the proposed model, we have considered this as the real infection rate, and the SIR model is predicting the some infection rate. The infection rate that is calculated by the SIR model was then corrected by the LSTM model. So this is the framework that is shown here. In this, we have used the infection data, the textual data. The textual data was provided into the PEN LDA models, and then the feature vectors were calculated from here. And in the infection data, again, we have calculated the features from here using the multi-layer perceptron. We have combined both the features, and then we have introduced these features into the LSTM model, which was making the prediction. And again, we were repeating the process until we have reached the minimum error. So the LSTM model is the one that was used to anticipate the difference between the actual rate that was calculated using the SIR model and the regression infection rates. So we have utilized the LSTM network for encoding the hidden states and the temporal information. In our model, we have used the single layer perceptron model to convert the infection rate and the textual features into the vectors. This is the functions that were used for the LSTM model, and the optimizer, the activation function that we have used in our model was the leaky relo function. And sorry. So this was the LSTM function that was containing the fully connected layer, and this is how we were converting the hidden states into the prediction. These were the results of our model. We have compared our results with the traditional SIR model, with the SIR LSTM model, where we have not used any textual feature. Next, we have used only the Twitter features. With the LSTM model, only the single online source we have used, and then we have compared when we have used the multiple online sources of the textual data. This was the result for the Maharashtra, and we can see that the R square and the value of the MAP is giving the best value we were getting for the using our proposed model. And same is the case with the Kerala region and Karnataka, and the last one is for the Delhi. So in the conclusion, we have developed a SIR based model that was incorporating the LSTM features and the data from textual data from the multiple social media platforms to predict the COVID-19 cases. And for the textual features, we have used the PEN-LD model, which was a feature extraction model. And later we have incorporated these textual features into the LSTM model to that has improved the prediction performance. The inclusion of these textual features has improved the prediction performance. So the model's prediction results are very consistent, demonstrating that the proposed model can forecast the infection cases, and the textual information processing of the related news increases the model accuracy. These were the references that we have used. So thank you.
Thank you, Akansha, for the presentation. So you have combined the SIR model with LSTM and other models.
Yes.
Still the R-square value is not very good.
Sorry?
If you look at the R-square value, it is 0.72, right?
Yes. Actually, it is not good. Actually, we are working on the we are improving this model by including the evolutionary algorithm that can improve the through which we can optimize the parameters. So we are working on the improvement of this model. In this, we have only just considered the SIR model. In our present work, we are considering the vaccination at the quarantined compartment as well. So the main motive of our in this paper was to see whether the inclusion of the multiple sources or the textual data improves the performance or not. That was the main aim.
How do you really choose the window size for the LSTM model?
Which size?
Window.
Sir, actually we have, yes, actually we have worked on the window size of 5 only. That was work in our cases, that was giving us the best results. So we have worked on that.
So your trial and error method you have used?
What I have used?
Trial and error.
I'm not getting.
Trial and error method you have tried, right?
Yes, trial and error method. Yes, sir.
Probably you should look at the autocorrelation and partial autocorrelation plot of this data, and then you can decide what should be the window size you should use. Okay, your current value depends on how many past observations, so that you get some idea based on the partial autocorrelation.
Yes, sir, you're correct.
Yeah, so you should look that and then make a decision on the window size.
Yes, sir, you're correct.
Because whatever number you have used for Kerala, Karnataka may not work for Maharashtra, because then each cities you have to look at the correlations, autocorrelation and partial autocorrelation. Okay.
Yes, sir. Actually, the news that we have considered is we have not divided the news with the state wise. We were just considering the news for the country wise, though we were taking the data state wise.
Okay. Any other questions to Akansha? Okay, thank you, Akansha, for the good work. And then
thank you, sir.
Rajan Singh, are you there?
Yes. So let me just share my screen. So is the screen visible?
Yes.
Okay, so yeah, so good evening everyone. My name is Rajan Singh, and my topic for today is exploring biomarker identification and mortality prediction of COVID-19 patients using ML algorithms. So authored by me, Rajan Singh, and Dr. Prashant Kumar Srivastav of IIT Patna. So this will be the workflow of the presentation. And rather than introducing the basics, like it's been 2 years since the COVID pandemic. So these all the information regarding that COVID is the respiratory is well known to all of us. So I will be just getting on briefly. So COVID-19 is a respiratory illness, as we know, and it was first discovered on 31st December 2019 by in Wuhan, China, and was declared as a pandemic on 11th March by World Health Organization. So till now, 270 million people have been infected with the virus, out of which around 5 million people have died. And we have seen even the countries with the good healthcare infrastructure like Italy and Germany weren't able to withhold the virus, and the infection rates and death were too much high. So new and innovative solutions like artificial intelligence, epidemiological models, and real-time tracking systems are being currently tried and tested all around the world. So for the motivation for our work, the sudden rise in the hospitalization requirements for the diseased patients caused an intense pressure on the healthcare systems, as we see in India as well in the second wave. So to counter this, early diagnosis and prognosis of the diseased patient should be the highest priority. Like earlier is the detection of the virus, better is the management of the spread. So with this aim, we try to identify the COVID-19 biomarkers. So biomarkers are essentially some biological factors that can be used to determine or detect the presence of the virus in a person, like if the person is infected or not, or what is the status of the person. So for this, we developed a machine learning based mortality prediction model using the identified biomarkers. So for the prior research, some of the several has been conducted, like not only for identification of disease or spread of the disease, several ML based researches have been carried out. One such was carried out by Yan et al., where they have used XGBoost, and there they have identified 3 features: the lactate dehydrogenase, lymphocytes, and high sensitive C-reactive protein as the feature to determine the biomarkers. And from then they developed a model which could predict the mortality of the patient with 90% accuracy and in 8 days in advance. So for that, and another work was carried by Karthik and al., where they have used 5 features to obtain an accuracy of 96%, and was able to predict the final outcome of the patient 16 days prior to their final outcome. So here is the research flow for our work, where we have taken the data of 375 unique patients. There were 375 unique patients with multiple readings, and the data size was 6,120, and the number of features was 81, out of which the class label, like the target label, was included in this. So after some data cleansing, we were able to remove the data points and reduce it to 18,060. And from there, we divided the data into 80 and 20% in the trained data set and the test data set. And then we developed a novel semi-automated data imputation technique in which we applied for both test and train. And for the trained data, for identification of biomarkers, we actually tried the sequential feature selection using the Gaussian naive Bayes as an estimator, from which we were able to identify these 6 out of the 69 available laboratory features. Out of 2 were prefixed. So then we selected these features from the data, and then we selected the data for train and test, and then we developed used the light GBM as a mortality prediction model, for which then we evaluated the model. So for this, in earlier works, what we have seen that the people, they have just directly applied the ML algorithms without considering the data imputation techniques. But in our work, what we tried to do, we put more focus on the data imputation technique. And for this, we carried out data analysis. So data analysis was done in 2 parts. Like for the qualitative analysis, we actually looked at every features, the biomarkers, and we studied in the context of medical terminology. The data had 80 features that were broadly of 3 types: 2 demographic, age and gender, while there were 74 laboratory tests and 4 hospitalization details. The target label was the final outcome, either the patient died or survived, and the 74 lab tests that were carefully studied with the medical significance. Now for this qualitative analysis, we looked at the data, like there were 375 patients, unique patients, as we told, and they had a lot of missing values, right? Like for every patient and every reading, not all readings were present, like it was varying. And originally the data had around 80% of the missing data. So proper handling of the data was carried out. So for data cleaning, of the 74 lab tests, 4 features were related to infectious disease such as HIV, syphilis, and other 2 as well. So we excluded these other infectious diseases because we could not be able to extend on the uninfected patient, while other biomarkers were continuous in nature, and we could basically extend to the other patients as well. So for our model, we fixed the detection text. Like there was a feature called COVID detection test that was used, and two more temporal features were added. That one of the feature was the difference between the date of admission to date of like COVID free and COVID free to a final outcome. So these two temporal features were added. So after that, the features were broadly classified into 4 types. First, the excluded features, the four aforementioned infectious disease, as I told. Then the primary features, which was 69 laboratory tests. Then the primary additional features, 2 added temporal, 1 COVID detection test, and 2 demographic, age and gender. While there were 4 additional features related to the time. So after some initial cleaning, the data had 5,300 samples with 78 features and 1 target label. And we then carried out. Like for data handling, actually, we looked at qualitatively these techniques, and we qualitatively applied on our data, like what are the advantages versus the limitation. So for, as we know, that dropping mechanism, it led to a lot of samples to be dropped. So that was the limitation, but it was a simple approach. While for mean and median, it was not considered because there were multiple, since it is a medical data, like taking the average of from 2 different patients would not be a better choice. Like if a person is suffering from another thing and the person, like it differs person to person. So that's why the mean and median was also causing a problem. Also, the temporal features that we added, we weren't able to extend to this. Now, the other was the last observation carried forward. Actually, it basically carries on the feature value to the present. So it basically, we looked at it and we saw that it does not include the effect of temporal as well. While the KNN imputation and the multiple imputations, they are not suitable for high dimension data. So considering this all, we developed a data imputation technique, and we designed it such as to keep the limitations of other technique. So the device data imputation has 2 steps. First was the manual feature categorization. In manual feature categorizations, the features were grouped in a some similarity based medical significance. While the second was the recursive subset KNN imputation, in which we recursively applied KNN to complete the data set. Now, this was the devised data imputation technique, in which there were the 69 primary features, which were manually categorized into features into 5 different levels. Not only groups, but we stratified the division. And we had those 4 features like the COVID detection test, age, and 2 temporal that were added in every iteration. So from here, we select the level. Then in the particular level, we selected the group, and we fed it to subset data selection. We carried out, in which we fed the original data. These 4 were fed into this, and from there we selected a subset data, which was fed into the KNN imputer, and we checked if the particular level, all the groups were complete or not. If it completed, then we selected on to the next level. If it was not, then we selected for the next group. And recursively, we selected the subset data, and we recursively filled the data until the complete data set was filled. So this was our data imputation technique. Now for manual feature categorization, 3 similarity factors related to the to the medical related terminology significance were considered. So since each of the 69 primary features uses some form of biomolecule or cellular measurement, the similarity factors were divided into 3 types. Basically 3 factors. So first was the function. Like for example, leukocytes. Leukocytes are they fight off the infection. So they have a generalized function as well as some specific. So this was the division of the function. While the type, like is it a biomolecule or is it an inorganic element like calcium or iron, and these were divided into that. while the third factor was the site, like a particular biomolecule is produced, where it is produced, and where is the site of action. So that was also included in the similarity factors. So in this, we, as I told, like we divided it into stratified manner. So in the first group, all the features were considered into a single group, and that was named as base level. While in the second, since we know that there are 11 organ systems, like a digestive system or the circulatory system, and in the so it was basically divided into 4 groups, and the site factor was used, like where from which is organ system it was used. And if we further divide, organ systems have particular organs. For example, circulatory systems has blood, and the heart and the arteries and veins. So for that, we divided it into 5 groups, and site factor was again used. Next was the division based on the function level, like what particular thing is does, like the leukocytes, they fight off the infection. So for this, function factor as well as the site factor were used, and 7 groups were created. And last but not the least was the response level. Like for coagulation, fibrin degradation products, basically it coagulates and or anticoagulates, like it stops the blood, or it allows the flow of the blood. So for that, 9 groups basically were divided in this level, and all 3 factors were used, function, site, and type. So next part was the data imputation, was the recursive subset data imputation. Basically, KNN imputer works well, but for higher, like where the data is a lot of missed, so there it causes the problem. So what we did, we instead of selecting the whole data set, we selected subsets of data, and then we applied KNN, which supposedly removed the limitation of the higher dimension or missing value, large missing values. So for that, since KNN is data determined, we reanalyzed the data and selected the proper data. So for reanalysis, the percentage of present data, percentage of rows, and percentage of unique patients were plotted with the number of least present features, like the number of features that each reading had, and this 3 factors. So after the analysis, the samples with at least 13 features were selected. The reasons were 2. First, the reason was that 13 was in the higher was in the region where the mentioned percentage plateaued. I will be showing in the next graph. And the second was that the maximum number of features in the manual categorization step was 12. Like in each group, there was the maximum that was present were 12. So, so we hope that by taking the 13, even if in a certain group, for a particular reading, even if 12 are present, then at least 1 will be from other group. So finally, the data selected was 1860 with 99.16 unique patients and 33.96 of present data. Now, this was the out of 356 patients selected, 195 survived and 161 were dead patients. So for the graph that I told about, we plotted the number of features that were present for particular readings, and we plotted the filled data cells for it. As we can see, like if we increase the number of features present for a particular reading, the filled data cell will increase percentage of, but the number of unique patients were decreasing, like we can see from the graph, while the percentage of rows was increasing. So we had to choose a place where there's some trade-off between all those 3. So as we can see, here is the plateau where all the all the 3 values plateaued. So from there we selected the 13. And for data splitting, we divided into 80:20 as I told, and this was some basic distribution of the trained data set where 353 unique patients were present with 58.
You should conclude.
Yes, sure. So basically, this was the distribution. And for feature selection, we used a wrapper-based method. So Gaussian naive Bayes was used, which gave a, it was used because it was significantly high performance than the other estimators. And the detection test in age were fixed for this, so as to include the comorbidities. And so the SFS was run from for all features, and I will just show the performance of the estimator. We can see that for 9 features it plateaued. So we selected between the 3 and the 9 feature as 6 because the performance was in between. And after that, we plugged into a mortality prediction model using light GBM. It is a gradient-based boosted tree. And after that, we applied the evaluation, and we got the following. We compared basically 6 of the algorithms. This is the same for the comparison of the performance with the increasing number of features. And for biomarkers, like after selecting, we analyzed, like we tried to take out the medical meaning. And first feature was lactate dehydrogenase, which is an enzyme which is released during tissue damage. And as we can see, the people who died from COVID primary and COVID complications had a higher number of lactate dehydrogenase as compared to the survived one. And we plotted it with the number of days to outcome and the value of the LDH. We can see there is a clear distinction between the survived and the dead patients. And the second feature that was selected during SFS was the neutrophil percentage. Here also we can see that the COVID primary and the COVID complications has a lot of difference. And so similarly, we plotted with the days versus the value, and we can see the difference like in the values. And the third feature was the fibril degradation product. And here also, like, there was not a clear demarcation, but still we can determine as we increase the number of features to be included, the demarcation decreased, like as visible from the graphs. And the fourth that was selected were the ESR. And here the COVID primary had a lower value than the other thing. And this is supported by some medical that we have referenced. As we can see, like the people with the COVID primary had lower values of ESR with the date. So results and discussion, like the light GBM outperformed the 5 algorithms, and using only 6 features, we were able to obtain accuracy of 98.66. And here are all the other matrices. And we also did the temporal analysis of the model, and it was able to predict for the survived patient in advance for 9 days, and for the dead patient in 6 days in advance. So this is the graph for that, and we can see that there is a skewness. It may be due to the presence of more data samples nearer to their death. So limitations, regarding the limitations, so certain limitations were regarding the data itself, because it has a lot of missing values. So we tried it on the simulated data, and the comorbidities and the unavailability of the treatment policies. That is also a thing that we are thinking of including in the future work. And the appearance of new variants like the Omicron or the Delta thing may show an unknown effect on the performance of the model depending on the mutated virus, like what it differs. So for this, the identification of COVID-19 biomarkers can be useful in reducing the immense pressure on the healthcare systems. The handful combination of 6 features, as we know, can be used in early and accurate prognosis of the COVID-19 patients. And this was it will be helpful in making quick and effective treatment policies. The future of the scope of the work may include the effect of comorbidities and other infectious diseases on the severity and the fatality of the COVID-19. So these are some of the references that I've mentioned in the slide. And thank you.
Thank you, Rajan. So you have identified the optimum number of features, and naturally it will improve the accuracy, right?
Right, sir.
So, but are we completely sure the results that we are getting is correct?
Yes, sir. For
So
that we need an
go ahead.
we required an external data set. Like the data set maybe it was from a particular like COVID speciality. So like we need a wide more spread data, which may include from other sources as well. So that is the thing.
Also, you may have to do some statistical test, and then are they really results are really significant? You have to analyze. Huh?
Right, right.
Any other questions to Rajan? I think people are getting tired towards the end. So thank you, Rajan.
Thank you. Thank you.
The last speaker is Satya. Satya, are you there?
Yes, sir. Yes.
Okay, you can. Rajan, you can unshare.
Yes, sir. Yes, I am on it. Right, sir. I'm just
streaming
Just hit on unshare, you know.
Oh, yes.
Satya.
Yes. Sir, my screen is visible, sir.
Your screen is not visible yet. Are you able to share?
Yes. 1 minute, sir. Just let me try, sir, once.
Only your video is visible. Are you not able to share?
Yes, sir. Yes, sir. I'm able to share.
Unable to share. What is the option? Rajan, you should sign out. Okay.
Yeah, now seen. We can see the screen.
Yes,
Rajan,
yes.
You can start.
Can I proceed, sir?
Yes, yes.
Yeah, good evening, sir. My name is
You have 15
Satyarajan.
minutes.
Good evening, sir. My name is Satyarajan Singh, research scholar, Computer Vision Group. Is it?
Satya, are you presenting?
Yes, sir. Is it slides
Why
are
are you not
moving?
presenting?
Is it now visible, sir?
Yeah, we told you visible. You present.
No, I'm getting later, sir.
Huh?
Yes, sir. On behalf of Rakesh Kumar Sanodia and Arun PV, I would like to present my part of my work, joint geometrical and statistical alignment using triplet laws of deep learning, deep domain adaptation. So my entire presentation will be classified into this is content-wise. I have introduction, related work, proposed methods, data set and metrics, experimental results, and conclusion and reference. So irrespective of the gender and education qualification and age group, everyone now you are using mobile phone. The main advantage they are going to take as a smartphones is camera. So by taking the picture, they are uploading multiple pictures at the same time. So the data of images drastically increases. How we are going to use those data, maybe for the entertainment purpose, or it will be for the technical purpose. So for when we are going to consider about the technical purpose, what kind of applications we are going to consider, like we have mentioned as face analysis, image retrieval, biomedical image analysis, handwriting transcription, transportation applications, agriculture, security and surveillance, digital assistance, manufacturing, assembling, ads, search, social media, in all automatizations techniques we are going to use for the image matching applications. Here we are going to consider one of application which we are going to consider as a face analysis. Why we are going to stress on face analysis is it's not a fun to say that sometimes I get confused to see my own picture in my Aadhaar card. Maybe it's not the case, all the applicable in all cases, but we encounter once in a while, so multiple reasons. Maybe because of diversity in photo shoot, the difference in two domains, and it maybe leads to misclassification of target samples. And one more reason is technical terminology, we can call it as a labeled information. So by considering the last criteria, labeled information, we have to move on to the next topic. Here, when we consider about supervised learning, with the availability of labeled information, we can easily classify face analysis or image retrieval concepts or classification applications we are going to implement. Now the criteria comes when we have lack of labels, what kind of work we are going to perform. That is a challenging aspect which we are going to perform. So in this criteria, we are going to use the term of domain adaptation. The main advantage of domain adaptation is we created a model with the help of a source labels. Based on the source label available information, we trained our model with the test target domain also. Based on this case, we are going to implement our model. So this is called as a domain adaptation. The domain adaptation mainly classified into two criteria, like a shallow domain adaptation and deep domain adaptation. The shallow domain adaptation will be simply consist of a less number of layers with the simple information retrieval or less number of features extraction purpose. We are going to use shallow domain adaptation. Here we already achieved some transfer component analysis, joint domain adaptation, subset alignment, semi-supervised transfer domain discriminant analysis. Like this, we are going to achieve some state-of-art experiments. But the limitations is the shallow domain adaptation cannot be useful or cannot be applicable for the complex features. Or else we can, if we are having more number of features, it cannot be able to extract the information with the help of shallow domain adaptation. Now consider about the deep domain adaptation, the second criteria. Here we are going to use these deep domain confusion method or joint domain alignment and discriminant feature learning that we are going to consider. Here we are going to use with the help of a loss criteria, minimization of losses, we are going to implement all these cases. This is the limitations that cases we are going to consider either subcentric loss or data centric loss or discriminant losses. We are going to use all these cases. To overcome these two drawbacks, what we are going to propose is joint geometrical and statistical alignment using triplet class for deep domain adaptation. Here our major now network, what we are going to use, the existing method is, at a time we are going to use two-stream CNN network. In this two-stream CNN network, we are going to provide the source image, source domain information and target domain information to the CNN at the same time. And we are going to identify the losses and criteria. So based on this losses availability, we are going to implement this case. So here our major constraint is we are going to increase the interclass discrimination, and we have to increase the interclass discriminations. So if we within the class discrepancies we have to reduce, and without in different domain classes we have to increase the classes. So for this case, what we are going to use, triplet loss we are going to use. The main concept is here we are going to consider one target. We are going to consider one anchor image. The anchor image and the same time, the same domain, same object image will be considered as a positive image. We are going to consider these two values, and at the same time, a image which is other than this mentioned object. So that will be considered as a negative image or negative picture. So based on these three values, we are going to create our triplet class. So this triplet information based on this triplet class, we are going to consider, and at the same time, what we are going to use is we have to, as I mentioned previously, we have to consider the two criteria, interclass discrepancies and intraclass discrepancies we have to consider. For this case, what we are going to use, we have to consider this loss function will be consider these two classes. For this case, MMD coral losses will be considered for this domain losses. At the same time, we are going to consider as a loss function as a for the cases. Here, by taking the hyperparameters, we are going to use these three values. Why we are going to use the hyperparameters? Depending on the data set which we are going to use, the values will be changes, and all these values will be considered for the cases. Here, the simple cases, by applying this case, we are going to apply on pi data set. The reason why we are going to use the pi data set is, as you mentioned, the same person, if we are going to consider with a different angle and force and light illumination constraints, the value will be changes. At the same time, if we observe in the bottom right, if the persons with the have same domain values, within the same domain value will be having different value for the other domain discrepancies also. So for this case, in the purpose, we are going to use as a pi data set, it consists of 68 people or 68 objects we are going to consider, and 40,000 facial images with 13 different poses, and 43 different considers will be considered. Among these cases, we are going to majorly consider C27, C5, C9, and C7 and C29 will be as our basic testing purpose. We have considered these 5 values. Based on these 5 values, we have done multiple experiments. So the main constraint is we are going to consider these values. One data C05 as a source and C07 as a target. We have to perform and we test our multiple cases. Same case, we are by altering the source and altering the domain values, we have to changes like all combination like 5 to 7, 5, 9, 527, 529, like this. All this indicates the values 5 is a left and left force, 29 will be right force, 9 will be top angle, and 7 will be bottom angle, C27 will be the center angle. Based on these combinations, we have applied all the values. So based on the existing available methods, we tested our model and we are taking the same values applicable. So here we are classified into shallow domain values, how these values will be executed, where at the same time domain adaptation, how our values will be executed. So we have mentioned our method with our quizzes. No doubt it will be applicable. In some combinations we have get the highest value, in some combination we are getting the lowest values. But on average, if we consider all the combinations, our method has got the highest value as 83.16 with comparatively other swallow and as well as the deep domain networks. So that depending on the force and depending on the illumination network, the values will be changes. But ultimately, if we consider the average value, we get this highest value will be considerable, sir. So by conclude this is, as a part, what we are going to case is the proposed method will be comparatively giving better results incorporating these 3 values like MMD and coral triplet values. It will be in the same single unified network we have implemented, and it will be providing same network. But in future, we are planning to extend our multiple, instead of taking as a single source value, we are planning to extend our with multiple source domains also, we are planning to adapt this ones. So these are the few references.
Thank you, Satya.
Yes, sir.
So you have considered the various data sets. I have some basic questions to you. What is the image dimension that you are considering here?
32 cross 32, sir.
So 32 by 32, that is 1024 features. So is it realistic? Currently,
Yes,
we are
sir.
not dealing with 32 by 32 images.
Yes, sir. Exactly, sir. In future work also, what we propose is we have to normalize the other data sets also. So initially we have to run on 32 × 32 only. But as you mentioned, in real world, we can't get this 32 × 32. That image size will be altered. We are running on other data sets with the other dimension also we are running, sir. That results yet to be we have updated, sir. That will be kept for the future work, sir.
So the 1024 features. So how are you going to reduce? What is the reduced dimension before applying your?
So initially we worked on
before applying the classification.
Yes, sir.
Before applying the classifier, what is the dimension? I'm asking.
It will be some images will be different images values, sir. Some will be the 128 × 128. Some we are having, some are 2064, like multi-dimensional, sir. So initially we have to consider only by 32 × 32 only, sir.
So from 32 by 32, you are going to 128 by 128.
No, sir. From 128 to 122, we are reduced that one, sir. If it will be changes, it will be value will be changes.
No, you are confusing me. So you said you started with 32 by 32 images, and then your deep learning network will reduce the dimension to a certain feature dimension, right? So that is the number, sir. I'm asking.
Yes,
so are those two CNN pipeline that you are showing, are the parameters are shared? Are you sharing the parameters?
Not, sir.
Then why is the diagram showing your line?
That will be calculating loss function calculation purpose we are going to use, sir. At the finally we are getting this value, sir.
Okay, Satya, thank you.
Thank you, sir.
So thank you, everyone, and that is the end of the day one. And see you all tomorrow at 9:30. Santosh, any other announcements?
Yeah. Tomorrow we will be starting the session by 9:30 sharp. So
yeah, that is a very, very, very important session. University of California, Davis, Professor Ian Davidson, and he is talking about explainable AI, where most of your work that you are currently doing, always you can make it explainable by adding or reducing the complexity. So it's a very important talk, and I would suggest all of you should attend at 9:30 sharp.
Yeah. Okay, so thank you very much, all the participants. We will see you tomorrow morning by 9:30. Thank you so much for joining us. Thank you, Jimson, for.
Yeah, thank you. Went well.
Okay. So